Hello everyone. Discuss contest what 16 already. So today contest was not as difficult as the previous one. Unfortunately, nobody solved the last problem. Okay, you solved it again at least. So last problem and you solved it. Nice. So last problem is not that difficult actually. So it is solvable this time. So last week we had pretty unsolvable problem, I would say. And now it's problem G. Okay. Today problem G is okay. Problem H, no, it's not impossible. So nothing that difficult happens in problem H. It's combinatorial problem. It's quite technical. Need to be careful. And there is strange special case. So that's why I get this +1. But overall solvable problem. So again, you can try to solve it later. Good problem about combinatorics. So if you think you need more trainings in combinatorics, H is actually a good problem to train combinatorics. Nothing that impossible. No special techniques used. Okay, all other problems I see pretty fine. Okay, a lot of people struggle with problem D for some reason. I don't know. Okay, we'll come to problem D and discuss. So problem A is pretty straightforward. You given some two-letter strings and you need to combine them to get another two-letter string. And you have only two options basically. You either contain exactly equal string in your set, or you have two strings which you can combine. Yeah, so in the middle you have the resulting string. So the first digit, or the first letter must be the same as the second one, as the second might be the first one. Yeah. So that's what I'm doing here. Just have small number of strings. I don't need to care about time complexity. I just 100 strings. So I just check all possible pairs here and see if the second letter is the same as my first, and okay, this should be A, obviously, yes, and the first letter is the same as my second. Then I can combine these two strings, and in the middle I will get the required one. I would say a pretty simple problem. Not okay. Sometimes we have just trivial problem. It's not trivial. You need still some programming here. You need to understand what cases you need to check. But it's how could say it's a good easy problem. Good problem to start a contest. Let's check if you had any. Some we actually struggled with. Actually, interesting. So what can go wrong? Wrong answer test 18. Interesting. Okay, so again okay, that's overcomplications. Overcomplications may cause some problems. Yes. So ouch. So you count how many times we have each. Only T0. Okay, so you count the first letters. Okay, if found, then yes. Okay, that's boring. Now we again scan all the strings. Remove the second letter. I think you probably don't. You don't want to combine string with itself. It's possible to combine string with itself. Yes, yes. So it should be yes. So you overcomplicate the problem for yourself. So that the problem allows you to have two equal strings. So you can combine string with itself. No, not here. It's difficult problem here. So we have AB and BA. Yeah, you combine them BA, AB, and you have the result. Why you have no? Why you have no? Because, okay, here we do something strange. Okay, so we remove this. Okay, so we find a string which have second character equal to the first character of the result. Okay, if it is true, we look at the second character. If it belongs to any string except our string, then we output yes. Okay, so what you plan... Oh, okay. So probably what you plan to do is to make 0 here, right? So because you added only first letters, so you added first letters, but you remove second letter. Doesn't make sense, yeah. So you probably what you plan to do is to remove the first letter, then check, then add it back. That would make sense. So it will be different problem, but makes sense. Okay. Again, careful reasoning of problem statement is important skill. Again, I failed twice during the contest. Twice I missed a important case in the problem statement, but yes, you get distinct fault with still possible. Unlock the font. You can. Yeah, it's hard to catch if you can use the same word twice or not. Can you check it by the examples? No, for examples, doesn't. Oh, for this example, for example, yeah, you may see that you see HA and then another HA, then you have like this. Yeah. Yeah, so if you read up to the end, so sometimes it's important to read all the all the examples and then the description of all the examples, because it will give you some important insights about what is problem actually about. Yeah, or just correct your understanding of the problem statement. Okay, let's move next. So that's the first problem. Pretty straightforward. You may have some mistakes, but overall, if you solved it, good for you. Second problem, what we have? Second problem is just a joking problem. So it's just a mathematical joke. You need to make square n by n so that sum of every row and every column equal to k. And okay, so I was thinking if I need to put different numbers or not. It turns out not. So if you look at the examples, you may see that you not okay. So you may use different or the same numbers here. So you 1 3 and 3 1, and you make use 3 3. So you're allowed to do anything basically. And the easiest solution, yes, is just to put all zeros and put number k on the diagonal. So this square will have some k for every row and every column. It's so that's the full solution. Very simple, but again, it's just mathematical joke. Sometimes problem authors love some mathematical jokes and they give them as programming problems. Some people think it's funny. I personally don't like that much. I think that like in programming competition, it's better than it is not mathematical joke, but some programming problem. So at least you need some programming or something. Here it's nothing, yeah. So okay, but okay, you failed it, so it's fine. That's fun. Okay, so you think sometimes it's impossible if n greater than k? Why? What's wrong with n greater than k? Okay, I think you just started from this use case. You just decide you will do this, and then you think what will you do later, and then you think this, and then you didn't understand that this is not longer needed. Yeah. Okay. Some mistake was again. You can make mistake in any problem, even in jokes like this. Problem C. Oh, problem C is interesting problem. So we have 14 holes. Yeah. So what happens? We take all the stones from one hole, distribute them among all other cells, and the score is sum of all even numbers after the distribution. So we have just 14 numbers, so we can check all of them. Yeah. Again, important thing is to check the constraints and check which constraints are small, which constraints are large. So if something is small, we can just brute force all cases. Yes. If something is large, we need to do something interesting. And here, like number of elements is small, so we can brute force everything. Yeah. But this number of stones in each what, how to call them? In holes. So number of stones in each hole may be large. Yeah. So this we cannot just brute force. Yeah. So that is again. So this constraint just tell you what you can brute force, what you can brute force. Yeah. So what we're doing here? Okay, I didn't have this picture, so let's have picture. So after, so we can brute force which hole we will use. Yeah. So so again you so we take stones from one of the holes, let's say I, and start and distribute them, yeah? And we distribute like this. We put here, 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 then here, 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 here. I don't know, it's not 14, but it should be 14, yes? And then we continue from here. Again, we start here, tum, tum, and again, and so on. Yeah, and we can't do it just using brute force, because there are maybe billion of these. Yes, you see this billion. So with maybe billion of these stones, we cannot just put them one by one. Too slow. Yeah. So this part we need to speed up. And you speed up very simple way. You just see how many full layers of stones you create. So number of, again, so if this number is AI, yeah, so number of full layers would be AI divided by n equals 14, yeah. So this number of full layers you do, and then you make something rest here. So size of this part will be AI modulo n. Yeah. So for these holes, you will put one more stone. Yeah. So by doing this, you can just in one swoop just calculate how many stones you put in each hole. Yeah. So that's what I will do. So first I just brute force which hole I take stones from, and then I just in a smart way calculate how many stones will be in each hole after I redistribute them, and then just using brute force calculate how many holes have even number of stones. Yeah. So again, you check which parts you can do in stupid way, which part you need to make in clever ways. So if something is small, do it stupid way. If something is large, you do it in clever way. Yeah. Just okay. So here I choose which hole I use here. Calculate how many stones in this hole, and then here I distribute all stones. So I take all. So here I do it. I calculate all shift. So J is shift from my stone. I calculate which stone will be in position J after position I. Put this many stones, and if it's less than this for the rest part, for the rest part of size modulo n, I put one more stone. Just okay. Here it should. Here I need to check. I take only from even. Yes, only from mod. And also this part should be J. Yes, we see. So this part should be J. Yeah. Okay. Unfortunately, the test didn't catch it, so I will get the wrong answer here. Stupid wrong answer. You don't need to do it like this. Okay, then I go read, so then I go back to it, read. Finally, okay, finally find. So actually, I feel like problem should be somewhere here, but I just don't see it. Okay. Yes, finally, finally I found this problem. Took me some time. Yeah, happens. Um, okay, because maybe it's because of strange namings here. No, okay, it's always it's always balance between good namings and like fast implementation. So yeah, I think it's not fast enough, but again, not ideal. Problem D. Problem D is it's interesting implementation problem. Not that often you have problem involved some clocks with handles. So I like this problem just because of that. It's not very usual, something like this. So what we have basically, so you after you read the problem, it's pretty hard to visualize what's happening, yeah. But then you have these pictures. Think of this for these pictures actually. Then you look at these pictures, and it's kind of more clear after that, yeah. So if you look at these pictures, you see that you have basically a circle. Yes, you have 3 handles in some positions, and you have 2 points, and you need to check if it is possible to move from one point to another point without crossing these handles. Yeah. So that's basically it. Again, if you think about it in terms of just numbers, so if it's not handles, just some numbers. So again, you have some chook handle, and you have some position here. It's called T1, and another position here like T2, and you have 3 points of handles. Yes, you have like X1, X2, and X3. And we need to check if it's possible to move from T1 to T2. So if it is possible to move here or here. Yeah. Again, if you split your circle anywhere, and you look at the segment again from 0 degrees to 360 degrees, yeah. Sorry. Look at all these numbers. No, let's look clockwise since we use clocks. Yeah. Normally I would do counterclockwise. It's mathematically just more natural. But again, we have x1, we have t2, so the t2, then we have x2, and then we have x3 and t1. Then what we need to do is just to check that we can move on this segment either in this direction, so we can look from here to here. So we need to check there is no points between t1 and t2. And we can move in another direction. We can move here and here. So we can do this if there is no point outside of this segment. Yeah. So if there is no points inside of the segment, it's okay. If there is no points outside of the segment, we are okay. If there are both points inside and outside, we're not okay. We cannot move. Yeah. In both directions, we will stuck. Yeah. That's it. That's basically the whole problem mathematically. Yeah. Now we just need to do careful implementation. So we're given these numbers as position of clock handles. Yeah. And what you need to do is transform this current time to position of the clock handles. And I do it, okay, so I do it just in doubles. So I was thinking about doing it in integers. It's possible to do it in integers. But since they promised me that numbers are all in the input numbers are small integers, yeah, I think I can do it in doubles because I will have enough accuracy to fit it. Yeah. So if numbers are not equal, and they promise numbers are not equal, yeah, then difference of two non-equal numbers will be pretty large. Yeah. So again, each number here is rational, and denominator is kind of small. You see, and the difference of two rational numbers with small denominators is pretty large. That's kind of idea. Yeah. So I decided I will just use doubles, and just it will make the code easier. It will make easier to write it, easier to understand it. And if you do the same in integers, it will be more precise. But I will spend more time just to figure out all these formulas and just debugging it. Yeah. So again, it's balance between nice code and fast implementation. Yeah. So I was here my balance moved here a little. Yeah, so that's my plan here, you see. So I transform my initial numbers to handle positions, and every position is like from 0 to 1. Yeah, so now I have 3 doubles in range from 0 to 1. So here I calculate position of the hours handle. Yes, it's hours plus 160. So every minute is 160 of an hour. Every second is 160 of 160 of an hour. So that's my total amount of hours, yeah, divided by 12 because I have 12 hours in full rotation, yeah. So now this number h is from 0 to 1. Unfortunately, so it is to 12 here, you see, not from 0. So it may be greater than 1. So I just do it like this to put it in range from 0 to 1. And do the same for minutes and seconds. It's much easier for these minutes and seconds. And just have the same for these two positions, T1 and T2. Swap them, so T1 is less than T2. Problem is symmetrical, so I don't care which one is which. And that's it. Just now I'll just okay. I will put them in array for simplicity. Yeah. And just I need to check if all numbers are inside the segment and if all numbers are outside the segment. So here I check if I have number inside the segment. Yeah. So here I check if the number is inside segment from T1 to T2, then okay, it's false. So if it's false, if it's true, it means there is no handle between the segment. Yes. So you can output yes. And then you do the same for outer segment. Okay, actually here I decided I just copy code twice for some reason. Yeah, so I decided I will just, yeah, I will simplify this part. So I count how many handles are inside the segment. And if I have 0 or 3 points, I'm fine. Okay, and here I forgot to say no. Yep. That's it. That's problem D. Uh, okay, okay. Now, let's read your solution. So that's my solution. So I just transform all numbers to doubles, put it here, and then check if all borders are between. Okay, if all these three numbers are inside the segment or outside of the segment. That's my solution. Let's check your solutions here. So you struggle a lot with problem D. Let's start from here actually. We're gonna answer 56 for a long time. That hurts. That hurts. Okay, it happened to me a couple of times. Okay, you're trying to do it in integers. I feel it. I feel it. Ah no, you did doubles. So why you have all these parts? Okay, you probably okay. It's probably not the first version. Yes, so you probably had some previous versions in integers, then decided to go to doubles. Okay, that's okay, that's something I do as well. Yes, you take h. Ah, you didn't do this part. Ah, is it the whole problem? Oh, that sucks if it is. H may be greater than 12 here. So, so you move it to 12 or not? Put it. No, you also have in different units. Ah, you divide by 5. Makes sense. Okay. So if h is greater than 12, h minus equal 12. Is it the whole problem? Okay, we'll see. So let's read someone else. What other problems you may have here? Test 5. What test you have? 56. Okay, let's wait. 56 again. Okay, so what's test 56? 158 43 12 to 1. No, it should be yes. It's a little bit greater than 1. It's much greater than 1, yes. From 12 to 1. Okay. So what else? What else could go wrong? Well, let's copy. Let's do it like this. Up. Does this part? Okay, if S is outside, and H is outside, and M is outside, then yes. Ah, 12. Okay, so they're both, so they're all inside in this test. So if this is inside, and this one is inside, and this one is inside. It should be yes. I don't see what's the mistake. Can you spot the mistake? This part is fine, this part is fine, this part is fine, this part is fine. Calculate maximum, minimum. Integer division by 5? No, it's no, they're all doubles. Okay, let's test then. Okay, so if we let's okay, it would be fun to just find the mistake, but if it doesn't work like this, we will just okay. Let's check if it gives me no. Let's see why it gives me no. Oop. It's much easier to debug when you know the test, right? Yeah. Um. Minute. Why my minutes are more than 12? Okay, like this. Yes. Yes. Okay. Yeah. You see, so you first need to add seconds and then scale it to the same. Okay. No. Yes, hard to find mistakes like this. Okay. Boop, boop, boom, boop, boop, boom. It's okay. It's just it's normal, very normal thing to have something. Again, I look how much time you okay. You spent more than an hour to find this problem. That may hurt. Yes, if you spend more than hours finding mistakes, like it's what I would do in this contest. So if I do something like this, so I will just skip this problem. Yeah. So after like somewhere here, I would just think, okay, let's wait. So you just put this problem away, solve the next problem. Yeah. So next problem is also not difficult actually. So it's which one? Oh, it's about trees. Okay. So some of these problems are also solvable for you, I believe. So you can just take this problem away, solve some other problems, then move back later with fresh head. Just read your code once again, scan every line carefully, see which one may give you a mistake. But yes, okay. Um, happens. Okay, so that was the mistake. Okay, let's move. So that's problem D. Problem E. Problem E is about DFS and trees. I don't. I'm sorry. I wanted to have special contest about DFS and trees. It's a very popular topic. Yeah, in many problems you have just some DFS on trees with some dynamic programming over it, some simple dynamic programming, or just simple DFS plus something. So happens a lot. So here we have pretty simple DFS without any complications actually. Let's open it. So what we need to do, we need to find all the leaves we can reach without seeing m consecutive vertices with cats. So basically we start, okay, so we have, here we have example. Let's use the example. So we have a tree rooted with node 1, and we need to check which leaves we can reach without seeing more than m like red nodes here, like so. Yeah, nodes with cats, and it's simple DFS basically. So if you think about DFS, what happens? You start from node 1, you go somewhere, and just recursively continue. And what you can do, you can remember how many cats you've seen. Yes, so if you seen some cats here, so here you just in this recursion you remember you've seen 3 cats. Yeah. So when you continue here, if it doesn't contain any cat, then you drop to 0. So you have current counter of cats. Yeah. So and if you have node with cat, you increase the counter by 1. Yeah. So you have your counter. When you move to your child, if it doesn't contain cat, you drop the counter. If it has cat, you increase the counter. And now you just in your DFS you have additional parameter. which counts how many cats you've seen. Pretty straightforward, actually, if you think about it. Okay, so let's let's skip this part. So this part is boring. So I just read the graph and call the DFS. DFS is very standard. I always write DFS on trees like this. I just add additional parameters. So I usually have two parameters, x and p. X is my current node, p is my parent. Yeah. I add another parameter, c. It's just my counter. Yeah. And just update DFS a little bit. So I see if I have cat, I increase counter. If I don't have, I drop the counter. Yeah, that's it. I update counter here. So when I enter the node, I update the counter. Again, just this very standard stuff. So I iterate for all neighbors. If it is not parent, then I go there. Yeah. If I don't have any children, I mark as a leaf. Yeah. So this boolean will be true if I never go to some child. So this should be x. This should be x. This should be greater than m. So if I have more than m, yeah, this should be greater than m. I will fix it. Luckily, they give us pretty good examples here, so I catch all my mistakes here. Yes, so here's a mortgage tube. Here I have this strange thing. It happens when you have actually when you have recursion overflow. So you see my recursion overflows. So it means I have some problem with my recursive calls. No, again, here I find what problem I have. That's it basically. Let's see your solutions. Okay, you didn't have any problems with problem C, so it's okay. It will be a little bit boring to see, but again, let's read what was your approach. Let's read Alexis, for example. Yes, pretty much the same. Yes, you have this parameters. You have. If it's not, okay. That's an interesting way to do it. Okay, so if it is 1, you make +1, and if it is 0, it makes it 0. Okay, that's too genius for me. I would make if statement here. Okay. Problem F. Problem F is not very difficult problem. It has some okay. So I made mistake because of some sort of word. Test 4. It's very strange corner case. Oh, you have different case. Interesting. And you have different. Okay. So we all had different problem. Problem F. That's interesting. My corner case is when you can put everything into single box, and you already have this box. So just the problem statement is like this. You need to find. Okay, so it's written very strangely actually. Is that to best way to put another magical box. So you need to find magical box which you can put everything you have. Yes, but sometimes you just already have a box and you put everything inside. Yeah, so you already can put everything. So the answer is not this box, but this box. It's just strange for me. It doesn't. It's not very logical. I believe it's not very for just for the legend of this problem. It's kind of strange. But okay. I admit you may read problem setting like this. Again, if I would be a problem setter, I would probably add this case to examples because it's okay. It's just not clear from the problem statement what you should do in this case. Okay, but that's me. So how I solve this problem? Okay. Okay, the idea is basically with problems like this is to go from small to large. Yeah. So let's take the smallest possible boxes. So you have some number of them. So you have some number of small boxes. Yeah. You need to put them somewhere. Yeah. So why not put them in a box one? So let's put them in a box of k. So of k. So this box is of 2 power k. So let's put them in box of size 2 power k plus 1. Yeah. And just count how many boxes do we need. Yeah. If we don't have enough boxes of size 2 power k plus 1, we can always imagine we have boxes. So if we don't have enough boxes, let's have some imaginary boxes here. So these 4 small boxes, they kind of work the same way like one large box. Yeah. So now again, so idea is to remove one side completely. Yeah. So I take the smallest boxes and try to remove them from this equation. You see? So I see what will happen to the small boxes. I either put them to some larger boxes, or I keep them as they are. Yeah. And if I have enough large boxes, I will just put everything into large boxes. Yeah. And now I don't think about the small boxes anymore. If I don't have enough large boxes, I can imagine I have some more large boxes here. Because these 4 small boxes, they always work together. Yes, you should never split these 4 boxes. So let's just group them and imagine that they are all together. Yes, so they behave like one large box. Okay. Well, that's it. So you move from pair KA to pair K plus 1 and like A divided by 4 sailing up. Yeah, something like this. Yeah, and that's how you remove one side of the boxes completely. Now the sizes here are maybe large, up to 10 power 9. See, so you cannot do it only. You can't increase size by 1. Sometimes you need to increase size by many. Yeah, so here you need to do some tricks. I don't like these tricks that much, but you'll see. So my initial plan was to do like this. So make map from size to number. So for every size here like this, for every size of the box, count how many boxes of this size I would have. Yeah? And again, just move items forward. Yeah. Then I decided I don't need this map. Actually, I will, since I need to move. No, okay, I can't move plus 1 size because I need sometimes. Okay, sometimes you need one small box and one very large box. Yeah. So like this difference may be large. So I can just increase, but too slow, because like size of the box up to 2 power billion. It's too much. Yeah. So what I would do instead, I will try to jump these long distances from small box to large box. Yeah. How to do it? Do the same thing. So again, you have current box of size k, and you have a boxes of this type. Yeah. So they're small boxes. And the next size box is like, let's say k prime. Yeah, it's the next size. So how many small boxes you can put in one large box? You can see that you can put like 4 power k prime minus k, that many 4. Yeah. That many boxes. Yeah. So you move from this pair to k prime and a divided by 4 power k prime minus k. Okay, let's write it like this better. Okay, so we can move plus, so k plus x. So after we move, increase size x times, yes, we will get a divided by 4 power x rounded up. So I have this number of them. Yeah. So that's how you can make this large step from small boxes to very large boxes in one operation, basically. I actually do it differently. I make one step, but I make one step only until I have only one small box. So I move from a to a divided by 4 to a divided by 18 to a divided by 18 by 4 is 4, 26, 64, and so on until I have 1. And when I have 1, I just have 1, 1, 1, 1, 1. Yeah. So I have this exponential decreasing sequence, and I just follow it until I have 1. And after I have 1, I stop following because I know it will always be equal to 1. So it's just following this sequence, you see. But at some point, it stabilized at position 1. So I follow this until I have 1, and then I know it will always be equal to 1. Many ways to do it. So here I decide to do not maps, but just basically stack of all elements. I will just take the last one, the smallest one, and move it. Well, here. So I take the last small. So last box is small. I sort them in decreasing order. You see, take the last box. It is the smallest possible box, and I look at the next box. So K2 is the next box, and I try to move from size K to size K2. And I do it one by one, you see here. So I try to increase the size of my car in the box, and A will be decreased exponentially, you see. So after some time, I either reach the desired size or I have A equal to 0. If A equals to 0, I also stop, yeah, because I know that I will always have one box. And here I just update the next box, like this. Okay, maybe not the most canonical way to do it, but it works. And here in the end, I look at the last box. When I have only one type, I do the same thing. So I try to put all the remaining box. I have all of the same size. I put them in one box. And here I have this problem, like I told you in the beginning, yes. So if I have only one box, I still need to put it in some bigger box. So I will have what, wrong answer test 4. It's nice because so they give you 3 examples, and it's test 4. So again, I try to scan everything, find what's the problem, scan this, scan this, scan this, scan this. Then I decided I spent too much time. I decided to actually, okay, spend too much time. I decided to find the test actually. It's cheating, I know. You can't do it. Sorry. But I decided I spent too much time on this problem. It would be not fun. So I decided I will go and look at the test. So that's the test 4. Very stupid test. So I have single box. I need to put it in larger box. So that's so I just do one step. So I move one of these steps outside of this if, you see. So I always make one step to the bigger box and then do it until I have one more. I don't like this. I don't like this detail. Let's say this problem. But you may have different problems. Let's see which problems did you have? Wrong answer test 5. So what is test 5? Billion 15 doesn't look correct. No, but billion. Why 15? X. You calculate maximum. It actually makes sense. So you can do it much easier, yes? How did you get 15? What? Ah, you're at P. What is P? K plus M. What is K? Ah, K is this. Ah, it should be X plus M, right? K is just number. Okay. Because you name variables in a strange way, so okay, yes, it should be K from the probability statement, but you named it as X. Okay. So is it the whole mistake? Yes, I believe it is. Okay. It's actually a much easier solution than mine, I would say. So what you do in this solution is okay. So we basically unify the size of all boxes. So in the fine in so if the final size, if you pick some final size, yes, like boxes of different size, they don't interfere. Yeah. So you have for each size, you need to have enough space to fit box of this size. So you have box of this size and box of smaller size. Yes. And the only thing you need is actually that box of each size just have enough space to fit here. Yes. Yeah, it may be easier to think of it like this. Yeah. It may be easier to think about this problem like this. Okay, not this problem. What's problem? F. Okay. Okay. So yeah, will make much more sense. Yes. So for each group of boxes, we just pick the minimal box which can contain them and just calculate maximum for this. Yes, this solution makes much more sense than mine actually. Now my solution also might make sense, but that's much easier solution than mine. Good for you. Good for you. Okay, let's go. We have two problems left. Problem G. Problem G. Problem G is actually a very nice problem of dynamic programming. How you see the dynamic programming? You need to calculate something modulo prime. Yeah. Usually it's either some combinatorics, so you calculate some factorial stuff like this, or it is dynamic programming. Old, good dynamic programming. Nothing fancy in this problem happens. So what we have in this problem? We just have situation when you have two elements, you have F and you have S. Yeah. And you kind of put these elements, so every time you put F, the next element should be indented in one position to the right. Yeah, so you have F, then you put S, then you can put here S and something like this. After you put S, you can move any number of positions to the left, actually. Yeah. So let's stop it like that. So so let's okay, let's try to simulate the process. So what we do, we just put these elements and we remember what is the current indentation. Yes. So like I. No, I is the let's say X. So X is my current indentation. Yes. So after you have variable F, statement F, for statement, yeah. So if it is indented by X spaces, then the next element always indented by X plus 1 spaces, yeah. So everything inside for statement should be indented to the right one position. If you have S statement, you don't care what's happened before. So if you have X here, it means you have some force happening here. At some point, you have some force here. So you can move to any of this previous force. So the next statement may be in every position here. So this new indentation may be any number from 0 to X inclusive. Yeah. So that's it. Again, what it tells you is after you play with this model, you see how it behaves. So So you see that this indentation, current indentation, so to check which indentation you can use, you only care about your current indentation and this problem and the statement. Yeah. So that's it. So you only need to remember what is your current indentation and look at the current statement. Yes. You don't care what happened before. So where are these four statements located? Yeah. So that's it. That's what we'll do. We'll do dynamic programming. Yeah. So for each indentation, remember how many possible ways we can do so we have this indentation here. Yeah. Again, one tricky part is here you need to add, you have too many transitions. Yes, from X to all previous elements. But we can do it using prefix sums. Yeah. So you need to add this element to all previous elements. It can be done using prefix sums. Okay, so let's go. So that's how I usually implement dynamic programming. I usually do it like this. So I have this one-dimensional vector here. It's my current layer of dynamic programming. Yes, and here I will just replace it with another vector. So every time I move to another vector of size n. So I make I don't make two-dimensional vectors because you need to think about memory and stuff. And here I don't want to do it. Yeah. So I just have one-dimensional vector for my current layer, and I move to the next layer. Yeah. So here J is my current indentation level. Yeah. I see if I have for statement, I move to level J plus 1. Yeah. So that's the thing. You have my plus equal J. That's it. And don't forget to calculate modulo. I decided to not use. So normally I have this structure mint which just have all arithmetical operation modulo something. Yeah. So I don't have to do it modulo mod every time. Yes. That's what and I still do it in the next problem, but I decided here I don't need it. But okay, I forgot I will need to do it in the next problem. So I will implement it, but not this. I will implement it in the next problem. Okay, yeah, and here I moves. So here, so I know this is n cube solution. You see, 1, 2, 3 loops. You see, it's n cube solution. It's too slow, and I need to speed up the solution. But I decided, and something I usually do, I first implement stupid dynamic programming, check that the answers are correct, and after I see that statement results are correct, I then implement some optimizations. Okay, so because it's very sad when you implement very sophisticated optimized dynamic programming and then it turns out your initial idea was wrong. Yeah, so I implement simple dynamic programming here, and then I will optimize this part. See, okay, optimizing this part is just technical. Yeah, so you need prefix sums. So you take prefix sums. So here I add to one element. So this element pj means I need to add to the whole prefix. Now I calculate sums. So I just push these values to the left. Again, it's very standard part. Yes. So you for each element you add it to all previous elements. So now you add this element to the whole prefix, and now just add these accumulated values to the next level. Again, if you don't know how to do it, just learn prefix sum. Prefix sum is one of the most simple and effective algorithms actually. So if you still don't know how to prefix sums, it's not hard thing. Yes. So again, how you use prefix sums? Let me show you. I don't have a lecture about prefix sums. I would just send you to one of my lectures, but I don't usually make lecture with prefix sums. You use prefix sums in two cases. So you have prefix sums when you need to calculate. So when you need to calculate sum of all a from L to R. Yeah. Yeah. So what you do, you calculate sums for all prefixes, and here you just need to take this prefix and subtract this prefix. I usually do it non-inclusive, exclusive side. So I usually do, so my usually P of R is sum of all A from 0 to R minus 1. And here I usually do R minus 1. Minus 1. This R is usually here, just for clarity, yes? So I calculate this prefix sum. So for example, P0 is always 0. So you don't need to have this special case. Yeah. And then how you calculate sum on every segment. Sometimes you do it in a different way. Sometimes you need to add to the segment. So you have operation A, so you need to take all elements from L to R minus 1 and make plus equals X. And you basically do it in the same way. So you take this segment. So for example, you can do what you can do. You can write, okay, depends on how you like to do it. You can put X here and minus X here and minus X. And then calculate suffix sums in the end. Just propagate these values to the right. Yeah, so here you have X, 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 and here you have X minus X will be 0, 0, 0, 0. Okay? Or you may do it on prefixes also. So you may calculate the same prefix sums, but now you can put minus X here and X here, and then calculate prefix sums on this array. So something like this. So some segment operations with sums, basically. So you can do it in both directions. Actually, the same thing happens if you know binary climbing technique. So so on a tree, you know, when you have a tree and something like this, yes, and there is binary climbing techniques, yes. So for every node you calculate like binary jumps. You jump 1 position, 2 position, 4 positions, and so on, yeah. And you also can use this technique to calculate some function on paths, yeah. So you can calculate for every jump, calculate some function like minimum, something like this, yeah. So you can calculate minimum on a path using this binary climbing technique without any heavy light decompositions and stuff like this, yeah. So if you have static tree, you have some values, they do not change, and you need to calculate function on some path, yeah. So sorry, I'm not good in drawing here. Function on some path. So you do some jumps here, do some jumps here, combine all these jumps, and get the final function, yeah. And you can do the same thing just to apply function to segments, yeah. So instead of calculating function on segments, you can apply function to segment. So for every binary jump, you can apply some plus X. Now, if I want to add X to this whole path, I add X here, add X here, add X here, and then in the end, calculate the result. Okay, just stuff to think about. So if you're curious, that's how you can do it. That's all. That's it. That's the whole problem G. Pretty standard dynamic programming, actually. Nothing fancy. Just standard dynamic programming. Let's read your solution. Okay, you have two-dimensional arrays. I don't do it because I need to think about memory. So here I have 5,000 by 5,000, 25 million elements. Okay, and my integers like 8 bytes. So 25 million by 8 bytes. It's already 200 megabytes. Yeah. And one array is okay. If you have two arrays, it's already, yeah. Usually it fits. Usually memory limits now are quite large, but still, if I can avoid this, I would avoid this. Here you do in opposite direction. Okay, so you do prefix sums and then apply these prefix sums here. Also possible, yes. So here you just apply prefix sums. Good for you. Again, so did you see? Yes. So I use prefix sums to apply values to prefixes, but Alexis uses prefix sums to calculate values of prefixes, because you can do both in this problem. Not on prefix, on suffixes. Okay, because you can do both. Yeah. So if you look in other direction, here, no, do I don't have. Okay, it's from previous problem. Okay, I erased it. So if you look in other directions, so what I do, I use forward dynamic programming. So this is my current layer. So this element affects all element on the prefix. So I need, like, if I value x, I make plus x on this segment, on the prefix. But you can look from other perspective, yes? So this is your current level, this is your next level. Yeah? So this element will be affected by all these elements, yeah? So all these elements will affect me. So my final value will be sum on this suffix. Yeah? It's the same thing, that's just in opposite direction. Sometimes it's easier to do it like this, sometimes it's easier to do it like this. In this problem, it doesn't make sense. That doesn't make big difference, yeah? So both approaches will work in linear time if you use prefix sums. Yeah, but sometimes one of these approaches is just easier to do, yeah? Good. Last problem. Okay, last problem, I don't like it that much, but it's okay-ish problem about combinatorics. Okay. I don't like these examples at all. In all these examples, we have m equals 2. That's, I don't know. If it is intentional, I just hate problem authors. If it's by mistake, okay, you need to be more careful. Because m equals 2 is very simple case, very special case for some reason, yeah? You may have at least what again. So my mistake was for case m equals 1. M equals 1 is very stupid case, but it is different. Yeah. And the general case is when m is large. Well, then you do something strange. So basically, you have different case when m equals 1, equals 2, m is large. So what's happening in this problem? So in general case, when m is large, yeah. So you have, okay, so any split, for any split vertical line, you must have the same number of different colors here and here. I initially thought you need to have the same set of colors, set of different colors. It's not the same number of different colors. It's number of distinct colors. Yeah. What does it tell you? So if you move this line left or right, yeah. So if you, okay, let's move this line to the right. Okay, let's start. Okay, let's start here and move this line to the right. So in the left part, the number will be increasing. Yeah, I only give more and more colors, and in the right part, it will be decreasing. Yeah. So if these numbers are the same, it means they are always the same. Yes. So if you have two functions, yeah, which are the same, one is increasing and one is decreasing, it means that functions are constant. So that's the important insight. Yeah. So this number should be just constant for namely for this position and for this position, number must be the same. So number of different colors here and number of different colors here must be the same. Yeah. Now imagine you have some X colors. So you choose some X colors and put them here and put them here. So some of these colors may be common, some of these colors are not common. Yeah. So you have some common colors here. So these colors are the same as these colors. Let's say you have Y common colors. And these colors are different. So you have some special colors here and some special colors here. Now, you can't use these special colors in the middle here. No, because then for one of the positions you have different. Yeah. So if you have some special color C, you can only use it to the right from this special line. So if you put like me, if you have this line, now you have this color C to the left, and now in the left part you have more colors than in the right part. Yeah? So basically what's happening? So I have some common colors, this Y, I can use them here, I can use them here, I can use them here in the middle. And I have some number of special colors which I can only use on the left part, and the same number of special colors I can only use on the right part. Yeah. And now we look at the constraints and see, can we brute force something? Yes, and them are pretty small. Yes, so we can brute force something. Yeah? So what I will brute force? I will brute force values of x and y. Yeah. So I will check how many different colors I have in the left and right part, and how many of them are common. So this common part. Knowing these values, I will use some combinatorics, some binomial coefficients to calculate everything. That's the plan. Okay. So let's see. Okay, here I'm thinking. Okay, what I did in this problem, actually, I read the examples first. Examples are pretty stupid here, but still they give me insight. So first I read this, not the number of different colors, but set of different colors, and then one of the examples was different. So okay, reading the examples and just checking that the answers produced are the answers I suppose they produce are actually helpful here. Okay, here I'm just thinking, too much thinking. Okay, let's start program. Okay, I start by implementing my whole model arithmetics. Okay, normally in a contest, I will just copy this from my library. Yes, I have all this in my library. I just copy this part, paste in my code, just use. Here I decided I will just implement it just for educational purposes. So what I have simple mint structure, which is just integer modulo something, yes. So I have this, and I have simple arithmetical operations. Then I need power modulo, yes. Just simple binary exponentiation. I use very stupid algorithms. I don't using anything fancy here. Basically inversion modulo. You just put modulo. You can do it for prime modulos. You can do it like this. And that's it. Now I calculate factor. Okay, I will calculate factorials later. Okay. I also need to calculate factorials modulo prime, but I will do it later. Okay, so here I check how many distinct colors I have, how many common colors I have. So this is total amount of colors I need. If it's more than k, it's just impossible. Now I need to choose. Okay, I think. Okay, here I need binomial coefficients. Okay, so I calculate binomial coefficients. So here I calculate factorials. Okay, I normally do it like this. So I calculate factorials just like this, and then I calculate invert factorials right to left. So I don't need to invert every one of them. Yeah, because inversions use in log n time. Yeah. So don't need to inverse all of them. I inverse the last one, and then go to the left. Yes. Normally to go from factorial to factorial, you need to divide by n. Yes. So yes, so we have one. Okay. I don't paper. So here I have n factorial. Here I need n minus 1 factorial. Yeah. Invert factorial. Yeah. So n minus 1 equals to this multiplied by n by n. Yeah. So I go right to left. This is how I don't need to divide. I need only to multiply. Yeah, just nice cheat I learned at some point of calculating factorials. So that's it. So I calculate factorials, and here I will calculate this. This actually I don't need this function anymore. So I can. Okay. So instead of calculating binomial coefficients, I will calculate some multinomial coefficient. Yes, that's what it's called. So here, what I need to do? Okay, yeah. So what I need to do? Okay, let's draw a better picture. So what I need to do? I have k colors. Yes, I need to choose some x of them to use in the left column, some another x of them to use in the right column, and y of them should have in common. Yeah. So I need x minus y colors only for the left part, then y colors common to the left and right, and another x minus y only for the right part. And I have something rest here. Yeah, it will be k minus all this. So k minus this minus this minus this. So k minus 2x plus y. Yeah, something rest. So here I need to split k into these parts. You can do it by calculating several Bayesian. So if you don't know this trick, let's learn it. So imagine you have some value n, yes, and you need to split it into three groups, A, B, and C. Okay, let's say A plus B plus C. And split the groups. How you usually do it? So you calculate binomial coefficient from, let's use, okay, it's not Russian notation, it's normal notation, yeah. So then you first you need to choose from A from B plus C. You need to choose some A values, yes, yes. Then from the rest, from B plus C, you need to choose some, let's say, B values. Yeah. But if you write it in factorials, what's happening? You have A plus B plus C factorial divided by A factorial B plus C factorial. And here we have B plus C factorial, yeah, divided by B factorial C factorial. And these factorials just eliminate each other, and you have A plus B plus C factorial divided by A factorial B factorial C factorial. Yeah. So that's how you calculate number of ways to split group into blocks of this size. So that's what I will do here. So I will calculate this k factorial and divide it by these factorials. See? So that's what's happening here. Yeah, I take one large factorial and divide it by these small factorials. It's number of ways to choose the colors. Again, it's pretty basic combinatorics actually. I use only factorials here. Nothing fancy happening here. But again, combinatorics is always kind of scary. Yes. Now it's tricky part actually. Now it's tricky part. I need to calculate number of ways to put these colors. So so if you look at the left column, so I need somehow to put here exactly X colors. So I need to color this left column so they have exactly X different colors. Yeah. And I don't know how to do it using factorials here. So I decided I would instead use dynamic programming. So here I use another dynamic programming just to calculate this thing. So yeah, so here I will calculate. So this D will be number of ways to color my column in using exactly I colors. So D of I is number of ways to use exactly I colors. Yeah. And that's another dynamic programming. Again, pretty standard, but again, yeah, it's like this. So imagine you already let me show what's happening here. It's easy. It's not that easy actually. So imagine you already colored this part, and then you add one additional element. So in this part you already used J different colors. So this J is number of colors. You see. So this next element may have the same color as one of these elements. Yeah. So if it is the same color, I have J options, and I again have J different colors. So that's the first line here. Yeah. It looks magical. Yes. dgj equals dj plus dj multiplied by j. Yeah. But that's it. Yeah. And the second line is when I use different color. Yeah. So when I use different color here, so it's some new color. So after that, I will have J plus 1 colors. Yeah. So any of these j plus 1 colors may be here. That's why I multiply it by j plus 1 here. Okay. Okay, a little bit magical dynamic programming, but yeah. So that's it. So in the end, it's again, d of x will give me a number of ways to color in exactly x colors. I decided I'll just multiply everything, so I have one big formula. Yes. So again, I need to get so in this formula, I need to choose colors. So these factorials are to choose the colors. Then I need to color left column and right column. And then I need to count everything in the middle. Yes. For everything in the middle, I count them anyway. So just use only these white colors. So I can use these white colors and doesn't matter how I color them. So it's just y power number of cells in the middle. Yeah. So that's the final formula actually. Uh, looks scary. Looks scary. Yes, but that's it. Surprisingly worked from the first try. I didn't expect it to work immediately. Okay, not that immediately. Here I forgot to initialize. Okay, here. Yes, you need to see. Because you can't initialize vector if you don't have default constructor. Doesn't matter. Yes, here I forgot to create the array. No, that's basically it. I will have wrong answer test 9. Again, I spent a lot of time looking for mistake actually. So no, okay, let's speed up a little bit. So I'm trying. So again, because I have very simple examples in this problem, or in these examples I only have 2 columns, so it's kind of boring. So I decided I will test it on some tests where I have 3 columns at least. Yeah. So spend too much time solving them manually. Okay. Okay. Later I decided I will go and look at the test. So the test doesn't work. Have only 1 column. So again, my solution assumes I have 2 columns. Yes, I color the left part, color right part, color everything in the middle. So if I have only 1 column, doesn't work. Yeah, because it's just very special case actually. So if you have only 1 column, you need to do something strange. So any coloring is good if you have only 1 column. Again, I don't like tricks like this. So again, if so when I'm creating problems, I usually try to avoid situations like this. So if there is some special case, it's better to show it in examples. Yeah, because it's a little bit cruel to do something like this to contestants. But yeah, who am I to judge? It's not my contest. Yeah. So that's it. So okay, again, it will pass all tests. So yeah, and it's pretty okay. You can it's 1.3 seconds, but time limit is pretty large. Okay, 5 seconds time limit. So pretty far from the time limit. Okay, that's it. That's contest 16. Hope you had fun solving it. Thank you for watching. See you next week.